Wavelength, very simple, is just going to be the length of a complete wave. The length of a complete wave. The unit we're going to use for that is some distance unit, some unit of length. So what do we use to measure length or distance? That's going to be meters, centimeters, etc. It just depends. A wavelength is the length of one complete wave cycle. So let's look at this. Wavelength is measured in many different ways. You can measure from end to end of a complete wave cycle. Remember, a complete wave cycle is up, down, and back. That's one complete oscillation. Wavelength would be measuring that distance. That would be a wavelength. You could also measure the distance from one peak to another. That would give you the same measurement. You could also measure the distance from one trough to another. That would give you the same measurement. Basically, if you choose a point on one wave and measure to the exact same point on another wave, that's going to be the wavelength. Don't get confused though. You must be able to locate one complete wave cycle, one complete up, down, and back motion. A lot of people miss that, and they are tempted to define a wave as up and down. That's only half a wave. So that would not be the wavelength, that would be half the wavelength. The whole wavelength is the distance of the complete wave cycle. You can measure it from peak to peak, from trough to trough, from equilibrium position to equilibrium position. It's totally up to you. That's the wavelength. Wavelength has an abbreviation. It is this funky symbol right here. This is the Greek letter lambda. It looks like an upside down Y. By the way, please don't get confused. All of these properties that we're talking about, they have abbreviations. Frequency is lowercase f. Period is capital T. Wavelength is lambda. And then they have units. The unit of frequency is hertz. The unit of period is seconds. The unit of wavelength is meters, which is abbreviated M, or centimeters, which is cm. So please don't get the abbreviations and all these letters mixed up. All of these have abbreviations, and then they have units, which also have abbreviations. I didn't tell you this one. Amplitude could be capital A. And what unit do we use to measure amplitude? Amplitude is just a height or a distance, once again. So it's going to be the same unit as wavelength. It's going to be meters or centimeters, etc. So please don't get all these units and all these concepts mixed up. These are the concepts. These are the properties. And then these are the units that we use to measure them. Frequency is lowercase f. It's the number of wave cycles passing through the substance each second. The unit we use is hertz, which is defined as per second, etc., etc. Find the speed of a wave. Sometimes you'll see it abbreviated with an S or a V. What do you think the V stands for? Velocity, yep. Remember, speed is the rate at which something travels, how fast it's going. That's really as simple as I can make it. How fast the wave energy is propagating through the medium. How fast is the wave energy moving? The unit for that's going to be some distance over time, typically meters per second. Hopefully you remember that from our very first unit, meters per second. There is an important equation for speed. Speed of the wave is going to equal lambda times the frequency. Lambda times the frequency. The wavelength times frequency. That will give you the speed of the wave. Let's see if that makes sense. Speed that we know is represented by meters per second. What's the unit for lambda for wavelength? Meters. What's the unit of frequency? Per second, right? So if you multiply them together, you would get meters per second, which is the unit of speed. And now we can start discussing behaviors of waves. Waves have very interesting behaviors. Besides the fact that waves cause particles to oscillate, waves themselves have very interesting behaviors that you must learn about. Reflection, refraction, and diffraction are the first main three that we're going to discuss, and you probably know these ideas already. Reflection is basically this idea that waves tend to bounce back when they hit a barrier or obstacle. Waves can bounce back, basically, and it's that simple. That's what reflection is. I want you to notice something. If I send a wave pulse through this string, you're going to notice something interesting. the wave pulse I send through is not just going to die out at the end. The energy is not all going to dissipate. Some of it will dissipate. Some of the energy will go into the clamp and into the air and things like that. I'm going to lose energy. That's called damping, by the way, when a wave loses energy to its surroundings. You can't help it. That's always going to happen. Just like the pendulum will not swing as high as it originally did because energy is lost to the surroundings through friction, things like that. That's called damping. Anyway, watch what happens when the wave energy hits the clamp at the end. So the wave is propagating left to right, it hits the clamp, and now it's coming back at me, right? It's being reflected. Waves can bounce back. Waves can be reflected when they hit a barrier. Just for the purpose of kind of showing this to you, let's add some extra energy. And I'm going to speed this up to normal motion. This is just pure wave reflection. Now, this is not what would happen in real life. In real life, the wave would be getting smaller and smaller and smaller until it completely went away. I have my damping turned off, so I've told this system not to lose any energy. What do you notice that's interesting about this reflection, though? Well, if the end of this medium, the end of this string, if it's clamped down, if it's fixed, then the wave gets reflected on the opposite side. That's very interesting. The wave gets reflected on the opposite side whenever both ends of the medium are fixed in place. I think that's kind of cool. What happens if I make this end loose instead? Oh, did you see the difference? If this end is loose, if it's free to do what it wishes, instead of getting clamped in place, then the wave energy gets reflected back on the same side, on the same side, on the same side. Loose-ended mediums, loose-ended strings, the wave gets reflected back on the same side. A fixed end, it inverts it. It gets reflected back on the opposite side. I think that's kind of cool. That's reflection. That's the simplest one. Refraction is the fact that waves tend to distort and bend when they move from one medium into another. Waves tend to distort and bend when they move from one medium into another. Here's an interesting example of refraction. Water waves. Deep water and shallow water. I can imagine that those behave so differently they can be considered different media. Do you remember what the word medium means? It's the substance through which the wave energy is passing. So what's happening when the wave energy, by the way, the peaks of the wave here are just indicated with these lines. The wave energy is coming in, it hits a new medium, shallow water. What happens to it? Well, it's bent. It's been bent. It distorts itself. The reason why is a little bit more complicated than I care to get into. It has to do with the fact that in a new medium, the wave will change speed. Anyway, you don't need to know about that. Just know that when waves enter new substances, new media, they tend to bend, they refract. Over here, this is quite interesting. Water waves cause erosion on the shores of beaches, and that erosion can take different forms, different shapes, depending on the depth of the water. Here we have shallow water. So whenever the wave is coming from deep water entering shallow water, the wave gets bent. And so you can see the wave kind of gets diverged. It gets bent this way and this way. It kind of converges onto this headland. That's actually what causes the headland. This gets eroded away more. And over time, the waves will erode this away. And that's all due to the fact that on the shoreline, going from deep water to shallow water, the wave refracts, it bends. Light does this. Light does this whenever it travels from one medium to another. I know that I've already told you that light does not require a medium. It's a little bit complicated. Light doesn't require a medium, but it can get bounced around through particles as if it's traveling through a medium. But let's imagine you have some water. The light wave is coming in. It hits the water at a certain angle. What happens to it? The water, the brand new medium, bends the light. This is why your straw in your cup looks bent. This is actually a major piece of evidence for the fact that light does behave like a wave. Light is what is transmitting images to your eye, and the light in the water has been bent because as it moves from the air to the water, then back to the air, new media, whenever waves travel from one medium to another, they bend, they get distorted, they refract. That's refraction. Finally, diffraction. This is the fact that waves tend to bend around and behind obstacles. Here's a great example. Let's imagine that you have some wave energy passing through and passing through a medium, and then all of a sudden that medium encounters an obstacle. Here I have two obstacles with a slit in between. So you can see that the wave energy, as it passes through the slit, it doesn't just go straight past through the slit in one little column anymore. Rather, you can see that it's bending back around to fill up the space where the obstacle was. So waves can bend around obstacles. This is lucky for us because radio waves, it turns out, as you will see later, are a type of light, a type of electromagnetic radiation. Believe it or not, radio waves are a form of light. They're waves, and they're actually pretty long waves. They're big waves, so they're really good at diffracting, bending behind large obstacles. So the radio wave is bending around the mountain, basically, around that obstacle, and whoever lives here, lucky enough, is going to get that radio reception. So waves can bend around and behind obstacles. That is the idea of diffraction. So we have reflection, refraction, and diffraction. The final wave behavior that I want you to know about is interference. And this is basically the idea that multiple waves in the same medium affect one another. They interfere with each other. And they do so in two ways, constructive and destructive interference. Constructive interference is when the waves are in phase with one another, their amplitudes combine to create a wave with a larger amplitude. Here's what I mean by this. When I say in phase, that means they line up basically. Peak lines up with peak, trough lines up with trough. The result is a larger wave, a wave with a larger amplitude. So here's what I'm getting at. We have multiple waves in the same medium, wave A, wave B. They can collide, interfere with each other, and here's constructive interference. I have a peak meeting up with a peak, and for a split second I get this larger amplitude wave. It turns out that the waves will just pass right through each other, which is interesting in and of itself. Let's look at this example. The two bottom waves are the waves that I have traveling through my medium, and they are in phase with each other. That means that peak of one lines up with the peak of another. And so peak plus peak equals bigger peak. Trough lined up with trough equals bigger trough. The amplitude has just gotten larger. So this is the result. This wave is the combination of these. This wave is the constructive interference result of these two waves. It's the result of them constructively interfering. Constructive, they go to build something bigger than themselves. This is constructive interference. The opposite is destructive interference. This is when waves are out of phase with one another and their amplitudes cancel each other out to create a smaller wave or no wave at all. It is possible for the waves to completely cancel each other out. What I mean when I say that they're out of phase is that peak lines up with trough, and the result is a smaller or non-existent wave. It is possible for them to completely cancel each other out.